Special relativity is the principle of uniform, linear motion, and the same physical law applies to light. This causes time to expand and contract. Light is emitted while moving. The speed of movement is v, the speed of light is c. The time elapsed when observed outside is t. The time elapsed for the person moving is t0. Light travels diagonally, and the speed of light does not change. T and t0 are derived from Pythagoras' theorem. This is how time expands and contracts. If the speed of movement is 60% of the speed of light, 1 second outside is 0.8 seconds for the person moving. I will introduce a method to verify the principle of special relativity. The upper line is the orbit of a geostationary satellite. A geostationary satellite is 36,000 kilometers above the ground, and its speed is 3 kilometers per second. The lower line is the orbit of the Earth where the Tokyo Dome is located. Let's assume that the speed of the Tokyo Dome is 400 meters per second. Then, a laser beam is irradiated from the geostationary satellite to the Tokyo Dome. However, the light is deflected and does not illuminate the Tokyo Dome. This is because, according to the principle of special relativity, the light travels diagonally and is deflected 360 meters forward. The diameter of the light spreads to a diameter of approximately 200 meters. The dome only travels 48 meters, so it does not illuminate. If that is the case, then this principle is correct. If the light illuminates the dome, this principle breaks down. What do you think? If this principle does not hold true, even if it is irradiated by observation, the dome will travel 96 meters, and even if the dome has a diameter of 150 meters, it will still be illuminated. I will show you how to verify the principle of special relativity. Attach a laser beam to a rapidly rotating table, with a mirror ball in the middle. The laser light shines on the mirror ball while it is stationary, and then rotate the table. If it is a high-pressure water current, the water will be deflected diagonally as the table rotates. So will the laser beam be deflected? Let's say the radius of the table is 1 meter, and the diameter of the mirror ball is 0.2 millimeters. If you make the table move at 30 kilometers per second, it will become pitch black. If you place a camera above and take a picture with the shutter open, you may be able to capture the deflection of the light. If it becomes pitch black, it is as per the principle of special relativity. If the rotation speed is 30 kilometers per second, but it is bright, this principle will not work. Is it possible to verify the special principle of relativity, using the photoelectric effect? Attach a laser beam to a rotating table, and shine the laser light on a metal needle. If it is stationary, electrons will fly out. Then shine the laser light just past the metal and rotate the table. If the radius of the table is 1 meter, and the part where the light is in contact is 1 micron, then, according to the special principle of relativity, the rotation speed is 300 meters per second. The light will be deflected and no electrons will come out. If this happens, then it will be in accordance with the special principle of relativity. If electrons still fly out even if the rotation speed is infinite, then this principle will break down. What do you all think? The principle of special relativity has undergone numerous verifications. Currently, the distance to the moon is measured using light from a satellite. Attempts are also being made with laser light from the ground. However, it is difficult to measure from the ground, because the atmosphere scatters the light. Therefore, the light is measured using a reflector on the moon's surface, 400 kilometers above the ground. Then, we verify whether the light travels diagonally from the satellite's orbit and the moon's orbit to the reflector, or whether it travels straight. What do you think? Do you know if it has been verified? The principle of special relativity has been proven by the Michelson-Morley experiment, but is that really the case? In 1887, a famous experiment aimed at detecting the ether wind did not observe the expected interference fringes. The shift in the interference fringes was evaluated as an error or 0. So, let's say the speed of light is c, the speed of the Earth's movement is v, and the distance to the mirror is l. Let's say the time lapse in the round trip, parallel to v is t1, and the time lapse in the round trip perpendicular to v is t2. For t1 t2 to hold, v0, that is, the speed of the Earth is 0, however, the Earth planet's rotational speed, orbital speed, and galactic rotation are all non-zero speeds. The shift in the interference fringes was observed in this experiment, and in subsequent experiments. Is the shift in the interference fringes zero due to an error in the equipment? In fact, the speed is not zero, so can't we think of this as the shift in the interference fringes? The shift in the interference fringes means that the arrival time of light is different, but is the arrival time of light the same? Aren't the interference fringes misaligned, because the light takes different times to reach the object? Does this experiment really prove the principle of special relativity? What does it mean for muons to reach the surface of the Earth? Muons are produced when cosmic rays react with atomic nuclei in the atmosphere. At rest, muons decay in 2.2 microseconds. In this short time, muons can only travel 600 meters, at close to the speed of light. According to the theory of relativity, muons experience time dilation. There is a diagram that captures the passage of cosmic rays through a cloud chamber by placing multiple lead plates inside the cloud chamber. The lead plates are miniature versions of the atmosphere. Muons gradually lose energy and slow down, don't they? In the atmosphere, muons gradually slow down and decay, don't they? So let's think about it this way. At rest, muons decay in 2.2 microseconds. They don't decay when they're moving at high speed, they decay when they're at rest. We measure the distance from the Earth to the Moon with laser light, and this technology is used to verify the theory of relativity. So, here's my theory: if we shine laser light on the lunar mirror, at the North Pole, according to special relativity, the reflected light will be off by 1,200 meters, because the speed of the Moon is 1,000 meters per second. The laser light is scattered in the atmosphere, and its maximum diameter is 1,000 meters. If special relativity is correct, there would be no reflected light at the North Pole. But if we shine light on the North Pole, that principle will break down. What do you think? According to scientific theory, how far can a spaceship be accelerated? The answer is close to the speed of light. But what happens to the speed of electrons in the atoms of the material of the spaceship, accelerated to close to the speed of light? The speed of electrons in the closest orbit to the nucleus of an atomic material, such as aluminum alloy, is extremely fast. Won't the speed of electrons in the direction of travel within the metal atoms of the spaceship exceed the speed of light? Also, what would happen if a gold coin was inside a spaceship accelerated to 50% of the speed of light? The speed of electrons in the closest orbit to the nucleus of gold is more than 50% of the speed of light. The speed of the electrons in the gold coin inside a spaceship accelerated to 50% of the speed of light would exceed the speed of light. There must be a mistake somewhere. The speed of electrons inside atoms is problematic in the classical mechanical model, but electrons inside atoms cannot reach the speed of light either. So, is there no time travel to the distant future or the past? According to the theory of relativity, significant time dilation occurs near the speed of light. Iron and zinc are essential elements for humans, and there are also trace amounts of gold and mercury in the body, but their electrons do not reach the speed of light. So, does that mean humans cannot experience significant time dilation or time travel to the past? Isn't Einstein's equation, which says time travel to the past is possible, wrong? What do you all think? If you found this video interesting, please subscribe to the channel and give it a high rating. Thank you.